Okay. So, hello guys. So I wanted to go ahead and create, do a kind of a live stream about, about, just kind of reviewing, functions and, for Calculus 1 if you're in Cal 1, or even for AP Cal if you're in AP Cal. And I am using, let me actually put, oh, and actually let me, this is wrong. It was, what chapter is this? It's chapter 1, but it's functions, I think it's functions and models. Yeah, functions and models. And I'm gonna try to go over as much of this as I can. I don't know exactly how many sections there are in here. Let me see. Okay. All right. Let me do this, and I'm just gonna copy this. Go ahead and copy this, and then paste it over here. Okay, and I'm gonna just do Okay, sorry about that, guys. And now what I'm gonna do Let me just go ahead and take all this off. Okay. Alright, so I'm gonna go ahead and just go over here and we're gonna look at, not this, take this off. We're gonna look at we're gonna go ahead and look at some review for calculus, or for from pre-calculus, and we're gonna look at this chapter here that is chapter 1, but it's basically kind of review from, you know, about functions, all that good stuff. And we're just gonna kind of go over this, and I'm gonna try my best to go over it as best I can, and not you know, not do too much either. So basically there's, you know, and the first chapter of this book, right, is functions and models, and we want to know, just, you know, and this is kind of a brief overview of, you know, what a function is, models, you know, and applications from college algebra. And I'm going to go ahead and read these following definitions, and I'm going to try my best to explain it in my own words. Like I said, these are not my notes. This is obviously from a textbook, but I did post a link in the description so you guys can take a look at it. So basically, we're going to just go ahead and read what this says, right? It says functions arise whenever one quantity depends on another. Consider the following 4 situations. So the first thing that they do, they talk about the area of a circle. Area equals pi r squared, and so r is the radius, and it's positive, right? And so a is a function of r, because, you know, we can say that, since, you know, it's a formula, but a is the output and r is the input, right? And that's kind of what they're talking about here. And also the human population, so, you know, they have this kind of this kind of t-chart here, or table, and they're saying that, you know, it depends on the time t, so the population in the world depends on whatever year we are in, or whatever year we are talking about in history. So they're basically just, you know, this is just a way to represent a function. And also part C talks about the cost of an envelope depends on its weight. So basically, however much it weighs, you know, it depends on how much it weighs. It's a so C is a function of weight, right? And then D, part D, it says the vertical acceleration A of the ground as measured by a seismograph during an earthquake is a function of the elapsed time. So again, this is, it depends on an input and an output. And it says each of these examples describes a rule whereby, given a number r, t, w, or t, and another number a, b, a, p, c, or a is assigned. In each case, we say that the second number is a function of the first number. So we're going to just go ahead and read this definition. A function f is a rule that assigns to each element x in the set D exactly one element called f of x in a set E. Okay, let me just explain what that means. So right here it says, we usually consider functions to be the sets of D and E, are sets of real numbers. The set D is called the domain of the function. The number f of x is the value of f at x, and is read f of x. So if you guys don't remember from algebra, from college algebra, we always read it f of x, f of x. I do have videos on that kind of stuff. And the range of f is the set of all possible values of f of x. So domain is always the x value, and range is always the y value. So let me kind of write that down. Domain represents x, and the range represents the y. This is the input, and this is the output, right? Okay. So we also call these independent variable. So the domain, we also call it the independent variable. I can't write today. Independent variable. And the output, the range, is the dependent. Right? Okay. So yeah, like it says for this example here, for part A, R is the independent variable, so the area is the dependent, and R is the independent. R is the domain, and A is the range of that expression or function, right? And then it says it's helpful to think of a function as a machine. So this is when we were, when in algebra, when they taught you about how a function kind of acts as a machine. You put in something for x, you get something out for f of x. And the machine is f. So basically, you get out something that's called f of x. So then let's see. The program functions in a calculator are good examples of a function as a machine. For example, the square root key on your calculator computes such a function. Right, and then it says, and enter the input. So if x is less than 0, then x is not in the domain of the function. That is, x is not an acceptable input. So if you guys don't remember, what they're saying there is, when you put it in the calculator, let's say I say the square root of, I don't know, -4, the calculator is going to say error or something like that, or it's going to say, like, it's not going to be defined, right? So what they're talking about here is that when you put in the square root of x and you put in a number for this, it has to be greater than 0. Or I'm sorry, it has to be greater than or equal to 0. That is what that is saying there. Another way to picture a function is by an arrow diagram. So this is another way to do it. So like they always, when we would always do when in algebra, when they would always give these they would always give kind of these things here where this was like called the domain, and there was another circle here and it was called the range. And what they would say is that every input in the domain had to have one output. But if, for example, let's just say, I don't know, let's just say, there's every input kind of has one output here. But, and also what could happen is, so for example, this is considered a function. Another thing is that if we have a domain and range, a list of numbers for a domain and range, let's say, I don't know, let's say 1, 2, 3, 4, 5, and let's just say there's 6, -2, 4, -7, and 9. And let's say that the domain is, let's say one of the x inputs, you know, basically 1 goes to 6, and then let's say 2 also goes to 6. This is still considered a function because it only applies, so an x value can have 2 y values if you think about it on the graph. Or I'm sorry, a y value can have 2 x values, excuse me. So if you think about it on the graph, let's say here's 6, and let's say that here is 1 and here is 2. If I plot 1, 6 and 2, 6, this is still a function because it follows the vertical line test. The vertical line test says that it only doesn't follow that rule if the line crosses it twice, and we'll go more over that in another, like in this chapter, I hope, later on. And so another thing is, says the most common method for visualizing a function is its graph. So obviously, you know, when we have a data table like this, or when we have some kind of data table like this, right, the best way to visualize that is with a graph. And it says if f is a function with domain D, then its graph is the set of ordered pairs. So basically, it's a graph. That just basically means that a graph, when you make a graph of any function, you're gonna always have ordered pairs x, y, and you're gonna be plotting those for every kind of function you make, right? Okay. And this just means x is an element of the domain of f of x, I think. I wouldn't think too much about that. It's just a notation. It just means basically, it's kind of like set builder notation. You know, I mean, I wouldn't overthink it. It's just another way of saying that x is in the domain, like it's all real numbers from -infinity to infinity. Okay. Let's see here. The graph of f also follows us to picture. Right, so right here it says the graph of a function f gives us a useful picture of the behavior or life history of a function. Since the y-coordinate of any point x, y on the graph is y equals f of x, we can read the function f of x from the graph as being the height of the graph above the x point. So this is the x-axis here, and this is the y-axis. When we have, for example, a point right here, that is what this notation would be. It's whatever, it's like, for example, 1, and then it's the function at x equals 1, whatever output value that gives you. That is what they're saying there. So let's go over some examples, and I'm gonna try to not over-explain it either. So obviously there are solutions here, but I'm gonna go ahead and, you know, we're gonna look at this. So find the values of f of 1 and f of 5, right? So you see here, right here, when x is equal to 1, it goes 1, 2, 3, and when x is equal to 1, y is equal to 3. So f of 1 has to be 3. And then when x is equal to 5, so 2, 3, 4, 5 right here, x is equal to about negative 0.5. It's like negative 1/2. You can't really see it, but you basically always, you know, let me just give another example. So like if I have, I don't know, some kind of curve, and I say this is, I don't know, negative 2 comma 1, and I say this is, I don't know, 2, negative 1, and I ask you, well, what is f2? And this is a function f of x, right? And I say, what is f of 2? Well, f of 2 just means, what is my y value when x is equal to, or I'm sorry, negative 2. What is f of negative 2? What is my y value when x is equal to negative 2? So what is y when x equals negative 2? That is basically what this is talking about. And so we know that when x equals negative 2, y is equal to 1. So f of negative 2 is 1. That is how you that is how you evaluate a function from a graph. And what if I say, well, if, let's say another example, right? And I say, here's 1, and I don't know, I'm gonna just name this a point. I'll put 1 here. I'll put 2. And I say, you know, like, I don't know. And I say, when, and let's say that this curve here, and I'm gonna actually color code it. Let's say this curve is f of x, right? So we define this by f of x. So when f of x equals 1, what is x? So when f of x equals 1, here's f of x, or y, right? Y is really f of x. It's the y-axis. So when y is equal to 1, let's just kind of make a line here. Where does it intersect? At what x value? Well, right here, it's 2. So when f of x equals 1, x is equal to 2. And that is how you would read the graph, right? Okay. And the last part they say is just basic interval notation. If I have a curve, let's just kind of say, I don't know, right here, let's do a curve from here to here, and I'm just gonna go like that. And let's say here's a point 6 comma 7, here's a point, I don't know, negative 2 comma 4. And I say, well, what is my domain here? What is my domain? Well, in interval notation, we have it goes from negative 2 to 4. I'm sorry, negative 2 to 6, right? And we have this closed dot here, which means that it is included in the interval. So we would say the domain is in interval form, it's negative 2 less than or equal to x less than or equal to 6. In interval notation, it would be bracket negative 2 to 6. And if they say, well, what about the range? Well, if you think about it, let's say here is, I don't know, let's say there is negative 3. And this is the lowest point that it goes to, right? That is the lowest y value that it goes to. Well, you're going to look at the lowest y value, and you're also going to look at the highest, the maximum, right? So basically, what is going to happen is you have, let's say this, for example, is, I don't know, 5, 10. And you're going to look at from the lowest y value to the highest y value. Right here is y equals 10. So the range really is going to be from, it's going to be -3 less than or equal to y less than or equal to 10. So in interval notation, it'd be from -3 to 10. These are just some very basic examples that I'm giving you guys. That is what it's saying here. So part B says basically, we see that f of x is defined when 0 less than or equal to x less than or equal to 7. So the domain is the closed interval, 0 to 7. Right? You can't really see it, but here is x equals 0, and here is x equals 7. Now from the range, here's a -2, and the maxima is at 4. So the range is actually from -2 to 4, right? So we have to understand when that happens and the difference, how to distinguish, right? Now it says sketch the graph and find the domain and range of each function. So I'm gonna just do this really quickly. I'm gonna draw a graph, and we're just gonna kind of go over this very briefly. So when we sketch so obviously, hold on guys, oh Lord, this is crazy. Okay, so all right, now this is, let's do 1, 2, 3, 4, 5, 6. Let's do 1, 2, 3, 4, etc. And then let's do -1, -2, -3, -4, etc. -1, -2, -3, -4, etc. Okay, and the one that they're asking us to graph is 2x minus 1. Now, if I do graph that, y equals 2x minus 1, first of all, we must understand the form, the slope-intercept form. This is so important for calculus, and this is very basic that we learned at the beginning of algebra. It's y equals mx plus b, where m is the slope, b is the y-intercept. And the y-intercept is of the form 0, comma b. Right? So, first of all, what is my y-intercept for this? My y-intercept means that when x equals 0, what is y? So, it's 2 times 0 minus 1. This is 0 minus 1, which is -1. So my y-intercept is at y equals -1. So I'm going to plot 0, -1 right here. And my slope is really rise over run, right? Rise over run. Since it's 2 here, I'm going to go up 2 and right 1. So basically what I'm going to do is I'm going to go 1, 2, 1. And I'm going to keep going. 1, 2, 1. 1, 2, 1, right? And that is how you would kind of, do that. And now also, I know that 2 over 1 is really -2 over -1, which means I can go left 2 and left and down. I'm sorry, I can go down 2 and then left 1. So I'm going to go 1, 2, 1. So this is right here. Oh Lord. 1, 2, 1. So then what we do is we just draw a straight line through the points. And that is how you would graph a linear equation or linear function, right? So that is the main idea of this. And also it says to determine the domain and range of each function. So we know that for a linear function, a linear function, if you guys don't remember, the domain and range to negative infinity to infinity. And by the way, guys, the parent function for this is y equals x. So it looks like this. It looks literally like a straight line through the origin. And again, the domain and range from negative infinity to infinity. And that is for how, you know, for functions, right? For linear functions. For part B, this one is a quadratic. So part B, kind of, it's a little different. But again, this is yet another parent function. So we're going to just do 3, 2, 1, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, negative 1, negative 2, negative 3, oops, negative 3, negative 4. Okay. Now, hold on, guys. Give me a second. Okay. So, okay, so here's one. My bad. My bad, guys. Hold on. So let's just quickly graph this so we kind of have, and so if I look at x squared, y equals x squared, right? Y equals x squared. And I'd make a table of values. When x equals 1, what is y? So 1 squared is 1. So I'm going to plot 1 comma 1. When x equals, let's do negative 2, right? Let's do negative 2. So when x equals negative 2, y equals negative 2 quantity squared. Negative 2 quantity squared is 4. So it's right here. And then when x equals negative 1, y equals the quantity negative 1 quantity squared. I'm basically plotting or plugging in this for x, every one of these numbers. So this goes negative 2, 4, negative 1, 1, because this is y equals 1 here. So negative 1 quantity squared is 1. So when x equals negative 1, y equals 1. And then when I do 0, obviously y equals the quantity 0 squared, y equals 0 here. And then when x equals 1, y equals 1. When x equals 2, y equals 2 quantity squared. So 0, 0, 1, 1, and 2. So y equals 4, right? So then this would be the parent function of f of x, and or f of x equals x squared. So the domain, obviously, now the domain and range for a quadratic is a bit different. The domain is always all real numbers. So there are no restrictions on this graph, right? So the domain is from negative infinity to infinity. But the range, look at our y value, right? Our y value starts at 0. It does not start, you know, below the x-axis. So our y value starts at y equals 0, and it just keeps going upwards. So this means that our range is going to be from bracket 0 to infinity, not, you know, not all real numbers really, because it only goes upwards like that, right? Okay. So right here. And also, guys, this notation is called set builder notation. Y such that y is greater than or equal to 0. It's kind of the same as interval notation. It's just another way to say it. But yeah. Now, let's do this one. If f of x equals 2x squared minus 5x plus 1. So that's another part of this. It's called the difference quotient, guys. The difference quotient. This is so important. for calculus. We are going to use this a lot. So there's f of x plus h minus f of x all over h. Oops. Actually, let me do it this way. F of x plus h minus f of x all over h. Alright. Now, let me kind of give a different example than the one that they're giving us, because, you know, I do have other examples. Let's do 2x squared minus 9x plus 1. And I want to find the difference quotient for this. And this is a function f of x, by the way. Now, I'm going to go ahead and we're going to do this very quickly. So the way that this works is you have f of x plus h, right? So f of x plus h, we're going to first evaluate that for this. And actually, let me put a instead. There we go. I'll put f of a plus h because I don't want to use x for this. So that means for every x value here, I'm going to plug in this. Right? So when I do that, this is what happens. I'm going to have 2 times a plus h quantity squared minus 9 times a plus h plus 1. This is 2, and again, if you guys don't know the sum of 2 squares pattern, or the binomial squared pattern, right? A plus b squared is always going to be a squared plus 2ab plus b squared. This will help a lot if you remember it for calculus. A lot of the formulas we learned in algebra and in pre-cal and trig, are going to help so much. It's going to be way better if you remember them, because if your algebra and trig or anything like that is pretty rusty, I would really recommend that you practice this a lot, because calculus has a lot of algebra and trig. Okay, so this is going to be a squared plus 2ah plus h squared minus 9, and we do distributive property, right? Minus 9a minus 9h plus 1. This is 2a squared plus 4a plus 2h squared minus 9a minus 9h plus 1, which is equal to 2a squared, and we have a 4a and a negative 9a, so that's going to be about minus 5a, and then plus 2h squared minus 9h plus 1, and then this is minus, and I'm going to do f of x, right? Because, or f of x. Or f of a in this case. Now f of a itself, we know f of x was 2x squared minus 9x plus 1. F of a is really going to be 2 times a squared, 2 times a quantity squared, minus 9 times a plus 1, which is equal to 2a squared minus 9a plus 1. This is going to be minus, and we're going to do parentheses or brackets like this because we're going to have to distribute that later. Sorry, guys. So basically, this is going to go minus 2. It's going to be minus 2a squared minus 9a plus 1. And this is going to be all over h. Now, let's go ahead and clean this up a little bit. So this is what we have so far here. This is what we have so far here. Now let's clean this up a little bit. So we have 2a squared. This part I'm going to keep the same. 2a squared minus 5a plus 2h squared minus 9h plus 1. And I'm going to distribute this negative in here. Minus 2a squared plus 9a minus 1. So remember that, guys. And then this goes all over h. So then finally, we see some things that cancel out here. So we're gonna cancel this out. And then finally, we're going to go ahead and cancel this stuff out, right? So then we have, or I'm sorry, not cancel that out. We're also going to cancel out this and this. So these two cancel out as well. What else cancels out? And now we have to combine like terms, actually. So we have 2h squared, because that is what this part is, right? And then minus 9h, and then negative 5a plus 9a, that's going to be plus 4a. Did I make a mistake here? Hold on. Minus 9a minus 5a minus 9 times a plus h, a squared plus 2ah plus h squared. I feel like I made a mistake here. I'm probably going way too fast. Hold on. 2a squared plus 4a. Oh, my bad. I meant to put 2ah, or 4ah, plus 4ah. I'm sorry, guys. I'm going way too fast here. I need to slow down. That's what happens when you go really fast. And in calculus, if you go too fast as well, you're gonna make a lot of mistakes. It's gonna go 2a squared plus 4ah plus 2h squared minus 9a minus 9h plus 1. And then obviously we're gonna do, so that's what that is, right? Equals, so this is gonna be what would it be here? I think that would be it for this, right? This is f of a plus h here. So that is f of a plus h. Now minus f of a. So f of a, we just did it. So now we have 2a squared plus 4ah plus 2h squared minus 9a minus 9h plus 1 and then minus, so we're gonna do, so it's f of a plus h, f of a plus h, this is what this is, minus f of a, so minus f of a, which is gonna be this part. So f of a, like I said, was this, that's f of a. Now minus the quantity, always put parentheses, 2a squared minus 9a plus 1 all over h. This is going to be 2a squared plus 4ah plus 2h squared minus 9a minus 9h plus 1 minus, distribute the negative, 2a squared plus 9a minus 1 all over h. This becomes, so we do this here, that cancels out, this cancels out, and this cancels out. So you have to kind of see your like terms very clearly. You have to kind of have a good eye for that. And if you don't, I mean, you can always just circle them, or, you know, to make it look easier, right? And then finally we have 4ah. So we have 4ah plus 2h squared minus 9h, and then all over h. And what is left over? Well, if you think about it, all of these have an h in common. We can factor out h. So we're going to do h times 4a plus 2h minus 9 all over h. And finally, this cancels out, so we are left with 4a plus 2h minus 9. And that is our answer. So that is what this consists of. This is exactly what I did, but with a different problem. That is exactly what they did here. Now it says here, there are 4 ways to represent a function. There's verbally, so description of words, basically. They do this a lot whenever they do applications. And there's numerically, so by a table of values. So a table of values is just like the t-chart with the x and y on the left and right. And then visually by the graphs, just like we did, you know, just like this looks right here. This part here, just like that looks. And algebraically by an explicit formula. So like we said, f of x equals 2x minus 1. You know, this is algebraic. Oh Lord. Okay. So, obviously, give me a second, guys. I'm sorry. Obviously, this is what, you know, the difference quotient is. In example 3 is the expression in example 3 is called the difference quotient and occurs frequently in calculus. As we will see in chapter 2, it represents the average rate of change of f of x between x equals a and x equals a plus h. So this is why we did this in pre-cal, because now, you know, once we get into since we're now looking at calculus, now we're going to see this play a huge role in calculus, and you're going to see it all over, like maybe in Cal 1 as well as I want to say maybe Cal 2. I can't remember, but also Cal 3. Cal 3, you see it a lot because Cal 3 you do basically limit what you did in Cal 1 and Cal 2, but what you do in Cal 1 and Cal 2, but it's in 3D. But I mean, that is a whole other topic. Okay. So this is kind of, if you guys don't remember, this function kind of looks like a either an exponential function, if you guys don't remember, an exponential function, and also I am going to go over like all the types of graphs and everything. Hopefully this book covers it, but I really have no idea. These are just some example problems. Hold on. Now we get to, so these are just some example problems about having, you know, making something, you know, as a function, right? Making, so it says, a rectangular storage container with an open top has a volume of 10 meters cubed. The length of the base is twice the width. So, material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Express the cost of materials. Express the cost of materials as a function of the width of the base. I know like this stuff here, this is length times width times height, obviously. And So it says the rectangular container. So let's just kind of draw this a little bit. I'm not going to draw it perfectly, but, you know, we kind of have this rectangular container. I'm just going to kind of, I don't even know how to draw it, Lord. But basically, you can kind of see what this looks like. And let me actually do a little snip here so that I can just kind of crop it and paste it, because I don't know how to draw this solid. So we're gonna go ahead and do that. And let's see. It's gonna be right here. And of course it, like always, it makes it very big. So what it's telling me, and what this is telling us, let's read it again. Material for the base costs $10 per square meter. So obviously we know that we're going to multiply these three things. The volume of a rectangular prism, or like a cube like this, I'm pretty sure it's a rectangular prism, is length times width times height. So we're going to do V equals H times 2W times W. This is going to be V equals 2W squared H. So using laws of exponents, obviously. And then it says it has an open top. So with an open top has a volume of 10 meters cubed. So we know the volume, V equals 10 meters cubed. And then it says the length of its base is twice the width. So I'm pretty sure, let me think. Oh, that just means this, right? The length, the width, right? L equals 2W, right? And so L equals 2W. And so W was, I don't even know how much W was. Let me see. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Okay. Material for the base costs 2 square meters. Costs $10 per square meter. Well, the base, I'm pretty sure the base, the length, the width, the area of the base. The area of the base is length times width, so it's 2W squared. And 2W squared, they said, is $10 per square meter. $10 per square meter. So it's $10 per this. So 10 times 2W squared is how much it would be. It's going to be 20W squared. And then it says material for the sides costs $6 per square meter. So the sides, which are I think it's considered, is it considered H? Or no, it's W times H. Okay. Okay. W times H. So the sides are W times H, right? So we can see here WH are the sides, and then so this is kind of how they work it out. To express C as a function of W alone, we need to eliminate H, and we do so by using the fact that the volume is 10 meters cubed. So they just kind of use algebra here to solve the problem, and this is kind of what we're going to have to do for some problems in calculus as well. It's a lot of algebra. Now example 6 says to find the domain of each function. Now we have the following, and we're going to go ahead and just look at this. F of x equals the square root of x plus 2. Oops. Now, if you guys don't remember, we can't have a negative in the square root. So when I say the domain of this, it has to be, so for example, I have to say that the square root of x plus 2 has to be greater than or equal to 0. If I do this, so if I solve for x, I get x plus 2, I square both sides, I get x plus 2 greater than or equal to 0. And then I go ahead and subtract 2 on both sides, and I get x greater than or equal to negative 2. That is how we know what the domain is. And in interval notation, this would be from negative 2, or no, let's say, no, yeah, negative 2 to infinity. Now, for the range is a little more difficult. So, the range, and actually, I don't even know if they ask for the range. Hold on. Oh, no, not the range, I guess. Yeah, no, never mind. They just ask for the domain of this. So, that is how you kind of, this is the domain for this right here. And that is how you would say it, right? And again, you have to know interval notation because, I mean, it's just going to be really difficult if you don't know how to do interval notation, how to convert an interval to interval notation, because we use that a lot in calculus. G of x equals 1 over x squared minus x. So all right. Now this one, when we have a rational function, we always say that the domain is, so if we have g of x equals 1 over, let's do u of x here, we say that the domain is x such that x does not equal whatever this like is whenever whatever x value this is when x is equal to 0. Let me explain. So what we're going to do here, we're going to go ahead and just make this not equal to 0. So we have x squared minus x is not equal to 0. And so we factor this out. X times x minus 1 is not equal to 0. We use zero product property. X is not equal to 0, or x is not equal to 1. Or I'm sorry, x minus 1 is not equal to 0. So then we add 1 to both sides, and we say x is not equal to 1. We know that the domain now is going to be the following. X such that x is not equal to 0, and x is not equal to 1. But we can write this in interval notation. So we can say that the domain is from negative infinity. We always say, so if it helps, you can draw a number line. Here's 0, and here's 1, right? You can draw a number line and say that the domain goes from negative infinity to 0, not including 0. So this is kind of the excluded value here. 0 to 1, so right here, 0 to 1, we use a union symbol, 0 to 1. Union, and then 1 to infinity. Here's infinity. 1 to infinity. This is the domain of the function, right? And so we have to know how to do that for calculus because, I mean, we do a similar method for finding maxima and minima, or the maximum and minimum values of a function, using this same kind of the same process. I hope I did the other one. Yeah. Okay, so yeah, so right here you can actually see that this is how it goes. Now, of course, we learn about the vertical line test, and the vertical line test tells us if f is a function or not. The reason for the truth, so this is the vertical line test, or let's read up here. The graph of a function is a curve in the xy plane, but the question arises, which curves in the xy plane are graphs of functions? This is answered by the following test, and it's called the vertical line test. A curve in the xy plane is the graph of a function of x if and only if if and only if no vertical line intersects the curve more than once. It says the reason for the truth of the vertical line test can be seen in figure 13. If each vertical line x equals a intersects a curve only once at a comma b, then exactly one functional value is defined by f of a equals b, but if a line x equals a intersects the curve twice, a comma b and a comma c, then the curve can't represent a function because a function can't assign two different values to a. Okay, let me explain what all of that is saying. And they even have a picture for this. What they're saying is, let's say this blue curve is a function, and we do what is called we draw vertical lines all over. And if we see that it only touches the blue curve once, then we know this is a function. On the contrary, if we see something like this, where we see this blue curve, right? And right here, we do a vertical line, a pink vertical line, at x equals some number a. It can be any number, right? And it crosses it twice like this. It like intersects it here, intersects it right here and right here. Then that is not good because it means that it is not a function, right? Okay. For example, the parabola x equals y squared minus 2 is shown in figure 14a. I'm sorry, x squared minus 2 shown in figure 14a is not a graph of a function of x because, as you can see, there are vertical lines that intersect the parabola twice. So, yeah, I mean, what this is saying is, when we look at this, right, what they're trying to tell us is, and we have, let's do x equals y squared minus 2. Let's say my function is y equals x squared minus 2, and I want to find the inverse. Hold on. Not the inverse. Hold on. I'm sorry. Let's say x equals y squared plus 2. Give me a second, guys. Hold on. X equals y squared minus 2. Excuse me. Okay. What they're saying is, if we look at that graph, right, obviously it looks like a parabola like this, something like this, right? And as you can see, if it crosses it twice, this is not a function. Now, algebraically, if you just are given this, y squared minus 2, if you're just algebraically given this and they're asking, well, is this a function or not, right? Well, I'm going to say, well, if I'm going to try to solve for x, or for y, right? I'm going to add 2 to both sides, and I'm going to say x plus 2 is equal to y squared. And we're going to go ahead and just take the square root of both sides. But when we take the square root of the left, we have to do plus or minus. So y equals plus or minus the square root of x plus 2. But the thing is that this represents y equals the square root of x plus 2, or y equals the negative square root of x plus 2. But we can only have one function of y. We can't have two. This doesn't work. So this is not a function. right? So just remember, anytime you see a squared or cubed or something with y, then most likely, like 99.9% of the time, it's not a function. If you see y squared like that. If you see x squared, I mean, that really doesn't matter, but if you see y squared like that, or y cubed, or y to the something, most likely it's not a function. But yeah, this is kind of how it goes here, right? It gives us these two different things, part B and C, where they were the square root of x plus 2 and negative square root of x plus 2, which that can't work. We can't have two different y terms, right? So it's not a function, right? All right, now piecewise defined functions. Now these are another type of function in algebra where we have kind of this, we have a function where it's in, that's why I call it piecewise, because it's in pieces. So, you know, it says a function f is defined by f of x equals 1 minus x if x is less than or equal to negative 1, and x squared if x is greater than negative 1. I'm going to do a graph of this, right? First, we're going to sketch a graph of how this kind of looks, right? Because I feel like this is so important to understand and review for Cal 1 and calculus in general, because, well, it's really good to know. So I'm going to do a graph, and I'm going to just go from, I don't know, let's do, Lord, how did they do it? They did, okay, well, they did that, but I'm going to go ahead and do my own, kind of my own thing here. So I'm going to go from, negative 2, negative 1, 0, 1, 2, this is 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Okay, so we're going to go ahead and do this, right? Now, this is, and I'm going to do my best to sketch the graph of this because I drew such a small graph here. Okay, so, alright, I'll put more, 4, 5, etc. It doesn't have to look exact. But our function is defined by f of x, and it is a piecewise, so it is the following, and this is what it gives us. 1 minus x such that x is, so 1 minus x such that x is less than or equal to 1, I think. Negative 1, excuse me. Let me write this down, like, actually type it down. Hopefully it'll look good. Let me just kind of get in here and do f of x equals, and I'm going to do this kind of like, I don't even know if I can, like, I don't think I can do that. I don't know. Because I kind of want to do like a piecewise, like, I'm going to just do it like this. So I'm going to do, actually, I'm not going to type it. I don't even know how to do it. But I'm going to write it down. So we have f of x equals 1 minus x, right? Such that x is less than or equal to negative 1.